Hello, this is our presentation on surrogate modeling of fluids for real-time control-based feedback. Um, our goal here is to combine CFD, which is computational fluid dynamics, with machine learning and bring computational fluid dynamics through machine learning into real-time applications. Included in our group is Jose Parra, Andrew Hembry, Wilson Kerr, and me, Sean Roskowski. No, due to some technical difficulties that the entire group couldn't get together and perform this presentation in one shot, so it will be separated into two MP4 videos. The first half is covered by me, and the second half is covered by Jose Parra. When I'm done with the first half of the presentation, there might be some technical difficulties with the MP4 video where the presentation continues going, but there's no annotation, and it goes through the rest of the slides without annotation. If that's the case, which will be after slide 15, then you could just ignore that part and then move on with grading and get to the second part. The second part should be named appropriately, such as machine learning feedback, MP4, part 2. So moving on with our presentation, what's the whole purpose of this project, this real-time controls-based fluid feedback? Well, in recent years, advancements in deep learning have sparked interest in applying data-driven methods to computational sciences and engineering. This shift has given rise to scientific machine learning, a field focused on solving domain-specific data challenges by merging traditional numerical methods with the predictive capabilities, interpretability, and domain knowledge offered by surrogate models. Neural networks are particularly valued for their ability to approximate high-dimensional functions in high-dimensional spaces. Low-dimensional functions in high-dimensional spaces, driving the development of new techniques to extract physical laws and domain-specific trends from numerical and experimental data. The Fourier neural operator is a framework for learning relationships between infinite dimensional spaces based on a finite set of observed input-output pairs. More specifically, let A and U be input and output observations in a normed high-dimensional vector space, which we refer to in our paper as a Banach space, and G, a model that maps our input A onto our output U. The goal is to approximate our model using a neural network trained on data sampled from a probability distribution over our input data A. Here, our model is a neural network approximation, which includes lifting operators that transforms our input data into a higher dimensional representation. This is through the use of things like fully connected layers and convolution layers. Our operator P projects it back to the target space, and within that network, we have activation functions and layers through kernel operators K. A key innovation of the Fourier neural network is its ability to parameterize kernel operators into the Fourier domain. By decomposing the spatial mappings that we get from fluid data into frequency components, the model can more efficiently capture far-field dependencies. Upon this transformation, learnable, what are called spectral, which is mainly referring to frequency weights, are updated, and the kernel operator is returned to the spatial domain. By combining the Fourier spectral layer with traditional projecting and lifting operators, as well as activation functions, the Fourier neural operator can leverage scientific machine learning techniques to efficiently model near-field as well as far-field flow interactions within a more computationally efficient framework. And this can potentially provide significant generalized approximations that are independent of numerical discretization and resolution effects that you traditionally see in these numerical approaches. So moving on to the Navier-Stokes equations. These equations are a set of very complex and highly nonlinear partial differential equations. They are bounded by physical continuities and are fundamental in fluid mechanics for their utility in simulating the macroscopic flow of fluid substances. For these physical continuities that we're referring to, we're talking about mass conservation. So mass cannot be created nor destroyed. Additionally, it can't, for example, when we talk about continuity, like disappear and be relocated in a completely different location. It needs to be transported. Then we have momentum. Momentum is conserved. So momentum is transferred. Momentum is mass times velocity, and it's transferred from one spot to another, and it carries a force or a moving force slash effect. Extending beyond this is the energy conservation. So again, energy cannot be created nor destroyed, and it cannot transport from one location to a completely different location. It needs to be transported within a field. Implicitly, the Navier-Stokes equations describe a mapping from input spaces such as initial and boundary conditions, as well as the aforementioned forcing functions and thermodynamic properties, to output spaces comprising of, for example, density, pressure, and energy fields over time. This mapping could be referred to as a Navier-Stokes solution operator. This can also be expressed as a traditional neural network and approximated as such as well. Through spectral representation, using the Navier-Stokes and Fourier neural operator, this data-driven approach can directly learn the trajectory of the Navier-Stokes equations, enabling rapid predictions of the Navier-Stokes equations in domains that are traditionally cost prohibitive when solved within a conventional numerical manner. For example, these equations, it's not uncommon for terabytes of data to be stored within a single time slice of a simulation, and this is commonly seen in practice. When considering that there's thousands, if not millions, of these temporal slices, we can see why there is a huge issue in terms of storing and solving these fluid problems in a traditional sense. In this work, we explore the application of the Fourier neural operator framework instead for surrogate modeling in real-time systems. We aim to establish a theoretical framework in solving deterministic problems by integrating data-driven surrogate models into real-time fluid dynamics applications. So previously, we have covered scientific machine learning and the Fourier neural operator. We covered how spectral representation of functions enable efficient computation. Neural layers mimic physical operators for real-time prediction. This has the advantage of speeding up simulations for real-time simulations over traditional solvers. And this has wide range applications. Here we're referring to control-based feedback systems, and we'll be testing it on a benchmark case as such. So as a summary, we discussed the CFD principles and surrogate modeling foundations, as well as the role of Fourier neural operators. Next, we discussed how we generated the data by performing CFD simulations and how we integrated it into machine learning processes. So as for our benchmark case, we have the mixing chamber geometry. To evaluate the performance of our Fourier neural operator, we conducted a transient fluid simulation of a laminar, immiscible water and oil species within a mixing chamber. The flow field was resolved using the Navier-Stokes equations as discussed, while the transport of the fluid primitive values such as density, pressure, temperature, and velocity were modeled using a volume of fluid approach. We'll discuss this volume of fluid approach as well as solving these highly nonlinear Navier-Stokes equations in the future. Within this problem, periodic boundary conditions were applied at the inlets, and the outlet was defined using a continuity enforcing constraint. We discussed these continuity enforcing constraints, conservation of mass, momentum, and energy. Additionally, rotating disks were incorporated within the chamber to promote mixing, with their boundaries handled using the immersed boundary method. This setup enabled a comprehensive assessment of the framework's ability to capture complex transient fluid phenomena. On the picture to the right, we see this mixing chamber geometry. The inlet and outlet, as well as disk boundary conditions are shown, as well as the overall geometry of the benchmark problem. It can be implied that the disks, inlet, and outlets, as well as the multiple fluid species, will generate a very complex fluid flow problem. This will serve to provide a stress test foundation for our neural operator architecture. As for our governing equations, we briefly touched on them before. So on the very top, we see what is the generalized Reynolds transport equation. This defines a fluxes of extensive properties and ensures that they are satisfied within the control volume. This yields the generalized formula with the partial derivative of phi over t plus nabla phi velocity is equal to the source term. This source term is zero for the case of conservation of mass. Mass is not arising out of nowhere. And we see that to the left when we see that the source term is zero on the right-hand side of the bottom left equation that is not in the box. And we see that the extensive property that's being conserved is mass, which we're referring to in this context as density. To the right, we see the conservation of momentum. Now we see that we have a source term. This source term arises due to inviscid and viscous forces, where the fluid is quote unquote losing momentum due to viscous forces. It's turning into heat, for example, due to collisions of particles. This is shown in the bottom with this tau expression, which shows the viscous forces that is affecting the fluid. These expressions can be simplified for the case of an incompressible fluid. In an incompressible fluid, there is no divergence in the velocity field. What this means is that for a specific volume, the amount of fluid going in is the same as the amount of fluid going out. This is referred to as a divergence-free condition. Plugging this into the momentum equation and plugging the mass equation into the momentum equation yields the equation in the top of the red box. This greatly simplifies the expression. Note another great simplification was inputting the Reynolds number, which is a dimensionless quantity that relates inertial velocity-based components with viscous friction-based components. This expression is much easier to solve, though still highly nonlinear. For the fluid and boundary handling condition, we used a volume of fluid method. The volume of fluid method was employed to track the transport of the immiscible fluid phases in the mixing chamber, using a volume fraction field to indicate the fraction of each cell occupied by the respective fluid species. The immersed boundary method was employed to model the rotating disk inside the mixing chamber. The immersed boundary condition approximates approximates non-equidistant and or non-Cartesian boundary conditions while preserving an equidistant and Cartesian grid. It does this by representing, for our case, rotating disks through marker points that describe the disk's motion as well as position. These marker points were used to enforce the no-slip condition by correcting the velocity field to match the rotational motion of the disk. This approach allowed for the inclusion of complex moving boundaries within the grid while preserving the equidistant grid. This is required for the Fourier-Neural operator, or is highly preferred because the Fourier-Neural operator works off of Fourier transforms and inverse Fourier transforms, which assumes equal distancing. For numerical schemes and methodologies, we used a lot of different numerical schemes and methodologies in order to accurately capture the complex movement of fluids. To enforce the incompressibility constraint, the stress terms were decomposed into their viscous and inviscid components. These terms were subsequently coupled through Helmholtz-Hodge decomposition, which is an iterative approach which projects the velocity field onto a divergence-free space. This decomposition ensures the final coupled pressure velocity field, which is our divergence-free condition, satisfies the incompressibility constraint. Within the equations, the convective terms were discretized in space using the fifth order Weno scheme. This scheme adaptively adjusts the nodes within our discretization grid while minimizing numerical dissipation in areas that are highly nonlinear and discontinuous. The diffusive terms were solved using the Crank-Nicolson scheme, where the diffusive terms were discretized in space using the second order trapezoidal rule. The inviscid and diffusive terms were spatially discretized using second order central differencing, which is a truncated Taylor series, while convective terms were discretized using fifth order upwind differencing, which is a higher order, again, truncated Taylor series. For the volume fraction field, given our volume of fluid approach, the inviscid, diffusive, and convective terms were integrated in time using the third order total variation diminishing Runge-Kutta or TBD RK3 scheme. This scheme begins with an initial prediction step based off of third order Runge-Kutta, followed by two successive correction steps to enforce our required total variation diminishing property. This ensures stability and suppresses numerical dissipation. For the primitive fields, the inviscid, diffusive, and convective terms were integrated in time using Adams-Bashforth. This method utilizes second order Euler's method to advance this solution in time while maintaining our temporal accuracy. So beyond solving these Navier-Stokes equations, here is a plot of our velocity or our volume fraction field. So this is the amount of water compared to oil. So 0, for example, is no water, all oil, and then 1 is all water, no oil. Here we see that the simulation is quite transient. It doesn't vary too much. However, there is still a lot of variation around the disk, and we see that it's clearly transient due to these variations. Here is our velocity in the x direction. We see some gradients in the disk, and that's due to the inverse boundary condition, but does not reflect fluid property. Rather, it reflects just the numerical schemes used and how these gradients are transported in the disk. They are irrelevant. Outside of the disk, we see how the fluid changes. We see some slight oscillation as time goes on. And this is the velocity in the y direction. We see the same trends as the u direction or as the x direction velocity. However, this is it's concatenated. Let's see. And here is a sample simulation that we have of this transient fluid flow problem to better see the complex fluid behavior. So here we can more accurately see the oscillations and the effects that the disk has on the velocity. Okay, and that is the end of my part. So yeah, if it keeps running on, there won't be any annotation, and this part is covered in the next section of this presentation.